Our first speaker, Dr. Lynn Orr, who was nominated by President Obama and confirmed by the Senate to serve as the Undersecretary for Science and Energy. Undersecretary Dr. Orr is the principal advisor to the Secretary of Energy on energy technologies and fundamental research initiatives, including DOE's programs in scientific computing. And so it will be it's very good to have him here on our conference. I was surprised when I read about Dr. Orr's background. So he's extremely well prepared actually for that role. So prior to joining the Department of Energy, Dr. Orr held academic and leadership appointments at Stanford University. He was the Dean of Earth Sciences, the founding director of the Precourt Institute for Energy, and the founding director of the Stanford Global Climate and Energy Project. Not only that, but he's also a member of the National Academy of Engineering, and he's a chemical engineer in training. So please join me in welcoming Dr. Orr on the stage for his talk.
Well, thanks, Bernd, for the introduction. I have to say that I'm sort of astonished and pleased that the two speakers this morning both have deep earth sciences connections. That shows a lot of good judgment on the part of the computing community. But my job today is not so much to talk about earth sciences. Instead, it's to talk about energy. And energy, of course, is woven through the fabric of modern lives. It's pretty hard to imagine doing what we do today without access to electricity, without a sort of endless weaving together of forms of energy and the ways we use them. So supplying that to the world in the future, but at the same time making it deal with the realities of the planet is something that we really all have to take on. Now, we start with some primary energy resource, and then we convert it into energy services like electricity and lights and heat and so on. So the question is, how do we do that, and how can we make all of that work better? We have done a couple of important reports this year. One, a quadrennial energy review that looks at the energy infrastructure for the country. And then we have a report that I'm going to talk about today, the Quadrennial Technology Review, which looks at the state of energy technologies and asks what the opportunities for research are in the future. So today what I'll do is talk a little bit about what we found, what the research opportunities are, and where we might go in the future. And I'll try to weave that together with a few examples of computing that is such an important underlying component of everything we do. It's worth noting that in the 4 years since the first Quadrennial Technology Review, a lot has changed. And so it's actually a good time for another such review. One such change is a big reduction in costs of renewable technologies like wind, and a big increase in deployment for those. Wind is up to 4.5% now of the electricity generation in this country, and the costs have come down. In the best resource places, they're competitive now without a subsidy. On the solar side, utility photovoltaics are now being deployed. Again, the reason for this is a substantial reduction in costs, and that's the result of lots of manufacturing experience, a lot of investment in China, a lot of research to reduce costs. And you might say, well, great, it's good, that's solved, we don't have to do that anymore. But the fact is that we can drive these costs down a lot more with additional research, so I'll say more about that in a minute. Those of us around the country who have installed PV systems at our home are also contributing. There's been a big reduction here in price and also a big increase in deployment. And something that I think is actually quite astonishing is that LEDs now have declined about 90% in price over the last 5 years. So that reduction really is tells you something about how costs can change with manufacturing experience. But since these things use maybe 15% of the energy that an incandescent bulb is, there really is a big opportunity to save energy and do good things along the way. And then in the battery side, electric vehicles are starting to take their place now. This is, again, the result of reductions in battery costs and improvements in energy density and power density. So the net result of all of this is that there's a lot of change underway in the energy landscape. The United States is now the biggest producer of oil and gas in the world. I think 5 years ago we wouldn't have anticipated that would happen. And then there's a lot else going on. So it's time to take another look at where we stand on all of this. So what do we want from an energy system? There are really three important components of this. One is energy security. Every society wants to be able to operate without the potential for disruption of the energy systems that they depend on. This means that it should be a diversified system. It should be diversified both on the primary energy resource side and also on the supply side. There's economic security, which means cost-efficient energy systems. Much of what we do in the research components on energy, Department of Energy, is aimed at reducing costs of systems so that our economy can be more competitive and provide jobs and be an efficient contributor to the economy. And then there's the environmental side. We know now that greenhouse gases and climate change are a substantial challenge, that energy is a primary way that we humans interact with the global systems that we, alas, take pretty much for granted. And that means that we need to do a much better job of balancing our use of energy with the climate challenge and with other emissions challenges that are associated with energy use. So those three things can go together. And I think what we should remember is that we now have this opportunity to create, manage linked complex systems that deal with all three of these challenges simultaneously. And it is pretty much impossible to imagine doing this without high-performance computing underlying much of what we have to do. So now I just emphasize again that this, what we have here is a snapshot because costs change, particularly with deployment. So the LED example that I gave you, 90% reduction in cost since 2008, that's just because a lot of manufacturing experience has been gained. But you see the cost curves here for the other technologies I've mentioned. Driving down costs makes it possible to do things in a competitive way that we couldn't do otherwise. But we should remember that this will continue, that this competition amongst energy resources and how they're deployed will continue in time. So it's actually fun to think about where things will go, but hard to predict. So some of you have undoubtedly seen a diagram like this. On the left side here, you see the energy resources: solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. To first order, petroleum is used for transportation, and the other fuels go toward electric power generation and direct use of thermal energy. So the Quadrennial Technology Review is kind of organized around this. The icons on the side: power generation is one, fuels is another. On the right side, they're the uses. And they're broadly distributed amongst buildings, manufacturing, and transportation. And in between those, the connective tissue is the grid. And by that, I mean the full transmission and distribution system. So that kind of knits all of this together. So I'll march through a few of these with some computing examples on the way. So let me start with the grid. Historically, we had a modest number of, well, thousands, but a modest number of relatively big power plants sitting on a backbone with largely radial distribution of electric power through the transmission and distribution system. It was minimally censored in the sense that it had, they had well, to give you an example, in the early 2000s, I spent a day at the California Independent System Operator, and in those days, it took them about a second to acquire the data on the state of voltage and phase angle and such, and then 3 seconds to compute the state of the system, and then they could think about whether an adjustment was needed, and so the cycle time for modifying, bringing generation assets on or turning them up and down was tens of seconds. But nowadays, especially with lots of intermittent renewables on the grid, the time scale for things to go south if something happens is much shorter than that. So that really was not an adequate control system. Now, when the financial crisis came in 2008, one of the ways we invested funds to kind of stimulate the economy was to install what are called phaser measurement units. These give you voltage and frequency and phase angle, and they're time synchronized so that you can tell where things are going in a certain place, and the information is gathered. This gave visibility for what was happening on the grid. And for example, the 2003 blackout that did occur because a line was overloaded and sagged and hit a tree and cascaded, that could have been stopped had we had these assets in place. So the message here is that we're partway through a big revamping, a modernization of the grid that's very important to our future. What we need to move to is a system that is flexible and resilient, can tolerate lots of renewables, has lots of sensors and data, which means that we also have to deal effectively with all the data. And it offers the possibility of automatic controls and optimization in ways that could only be dreamed about even just a few years ago. That's a work in progress, and we need to do much more. You can imagine microgrids that are islandable so that they can operate even when Hurricane Sandy has knocked some pieces offline, and they can recover much more quickly. The millions of smart meters that have now been installed actually are sensors that tell you where things are operating or where they aren't. You can nowadays, so when the tree fell on the distribution or the feeder line before, the way the utilities found it was, first of all, they waited for somebody to call them and complain, and then they sent the truck out with the flashlight to look at the wires until they found the one that the tree fell on. You can actually do that in a communicating system. You can do that automatically now, go right to the spot where it happened. So it's more resilient even now and can be much better in the future, particularly as we begin to manage this much more complex system. So in terms of the renewable side of things, we actually have to pay attention to the fact that the resource is not uniformly distributed in time. These curves show the top two show the net load curve in the California Independent System Operator territory for 2012 and 2013, and starting with the curve that's labeled 2014, this so-called duck curve shows you the effect of big solar generation in the daytime. Now, that's great, lots of solar power into the system, but a pretty big ramp rate, 13,000 megawatts in 3 hours as the sun gets low on the horizon. So managing deep penetration of renewables, being able to operate complex systems of assets is going to be a challenge that we have to work on as well. Storage is another aspect of this. Electrons, for the most part, our grid is one that's been balanced with generation and load matched as closely as possible. In a system with much more intermittency involved, storage would be useful, and storage on a variety of scales. On the small scale for transportation, batteries look like the right solution. In the intermediate scale, things like flow batteries offer some grid scale storage. And then there's pumped hydro and compressed air storage for larger scale systems. Lots of work going on in this area, lots more to be done, lots of research opportunities here. So assuming that we now have set in motion the kinds of things that we will need to do for clean, for a grid that can manage all this clean power, now we better generate some of the clean power. So let me say a few words about that. Right now, the coal generates about, I call it a third, a little more than a third of the electricity. That's actually down. Competition by low-cost natural gas has made it harder for the older, least efficient coal plants to compete. And the new rules for carbon emissions and other things like mercury emissions will change the landscape as well. This is a picture of a plant where a large-scale carbon capture and storage project will be installed. And it's pretty clear that we can separate CO2 from combustion product streams, or alternately, we can separate oxygen from nitrogen and burn with pure oxygen, so you make CO2. Cost is the issue. These things, we separate commercial quantities of CO2 from other gases every day in refining and natural gas processing operations. But we're talking about a much bigger scale, and we need lower costs. So the research opportunities include better separation techniques and the ability to predict where these fluids will go in the subsurface if they're injected. So big computational opportunities there as well. Now, one of the things that has to happen, with a little luck, that was supposed to be a video that started back there, but since I can't go backwards, there we go. Now, if we, well, maybe the video will start. But in any case, what happens, there we go. That CO2 that gets separated in the power plant then needs to be compressed to shove it underground. And these compressors that do this, they consume lots of energy. It turns out that the details of how vortices shed at the tips of the blades, those can be controlled with something like tip injection. They offer some real opportunities for both better efficiency and technologies that can allow us to make better jet engines or gas turbines as well. So it's a place where the combination of very high resolution computing, high resolution both in time and space, can help us manage in this case, the shocks that control angle of attack on the turbine blades, which in turn controls efficiency and either delays or helps produce turbine blade stalls that can cause problems. So a real opportunity for high-performance computing to make it all work better in the future. On the nuclear power side, we have about almost 20% of the nuclear power in this, 20% of the electricity in this country is generated by nuclear power now. We have 5 new nuclear power plants under construction in the U.S., so there has been a bit of a renaissance there. Cost is still an issue. Spent fuel storage is an issue. And the future includes some possibilities for small modular reactors, fast spectrum reactors that can change the waste storage picture, and lots of materials questions that have to do with life extension of the existing power plant fleet. This picture is one of a small modular reactor, and the image on the right is a picture of results from a project that is looking at in detail at modeling at very fine scale the performance of a nuclear power plant. This is an opportunity to improve performance with detailed simulations. The problems are fundamentally multi-scale and ones that have lots of potential for improvements in efficiency. And speaking of efficiency, the turbine I talked about a minute ago was one that was for compressing CO2. This one runs the other way. So the turbine on the left side in this is a steam turbine They are everywhere in the power generation system. It's two-sided, it has 5 big turbine wheels, and the image of a person there gives you some sense of the scale. That one's a 300 megawatt turbine. On the right side is a 300 megawatt turbine that uses supercritical high pressure CO2 as the working fluid. So turbines are just wings, and mass flow over the wing is what generates the thrust that either keeps the airplane in the sky or makes the turbine turn. If you have a denser fluid like supercritical fuel CO2, then you can make the turbine smaller. Now you say, okay, great, I'm sold. Why don't we have these things everywhere? Well, as you can imagine, there are some technical issues to be sorted out. Many of them have to do with the material science of all of this, so our ability to calculate and predict properties of materials in advance would help a lot here. On the wind power side, wind, as I already said, has really come down in cost for the best areas. And we really have spent our lives modeling what happens at a single wind turbine. But in fact, people don't usually build single wind turbines. They put them in wind farms. And depending on which way the wind is blowing, the turbines can be partly shielded. But what a very interesting computational exercise has shown is that with some combination of control over which way the turbine angles and the blade pitches, you can actually steer the wakes a little bit. And even just a little bit of steering can give you, in this case, a 14% improvement in the energy capture from that wind turbine without rebuilding anything. But it really demands the computational resources for a big system at fine scale to be able to do this appropriately. On the solar side, again, big reductions in cost, but lots more that we can do. There's a host of new materials coming along that offer potential for much lower costs. And to be fair, there's room to do better on the soft cost side of what it costs, the balance of system, the permitting costs, and those kinds of things. It costs about twice as much to install a solar PV system in the U.S. as it does in Germany, for example. So we can do better. So that's likely to be a resource that will contribute much more in the future. So let me say a word about transportation and vehicles. So vehicles are ubiquitous. I mean, we all think we need to have multiple vehicles that we own, which mostly sit around not being used 98% or so of the time. So there's a whole host of opportunities to do better there. Now, the one great thing about liquid fossil fuels is that they pack high energy density, so you can put gallons in the tank and go a long way. You can imagine electrifying some of the urban transportation effort, for example. That will require better batteries and lower costs. But still, for the long haul, trucking and probably for airplanes, combustion is likely to continue to be an important component here. So combustion efficiency is a research opportunity, thinking more carefully about co-optimizing fuels and engines, light weighting. Reducing the weight of what you push around either through the sky or on land offers a big opportunity there. That's fundamentally, again, a materials problem. Can we make lightweight, strong, safe materials that do the job? Various versions of electrification could be batteries, could be fuel cells, and so on. Lots of opportunities there. And then we can think about the systems aspect of all of this. All of us get in our car, and even now you can look at one of the mapping software systems and have a shot at figuring out where the traffic jams are. You could imagine that our vehicles are going to help us do that more carefully in the future, and thinking about the systems aspect of how that works offers some opportunities as well. On the advanced manufacturing side, I have to say this was an area that I knew less about when we started working on this than I do now, and I'm really quite excited about the opportunities here. So this is a 3D printer making a car. It's sort of a rudimentary car. That version turned into this. And then that turned into this. Those of us who are from my area will recognize the Shelby Cobra had a 427 cubic inch piston engine in it, but this version is electric. And what's interesting about this is this vehicle went from drawings to that car in 6 weeks. So it was a 3D printed car. And it makes the point that by judicious use of a combination, you can't do this without lots of computing, by the way, judicious use of our ability to translate computing into making a part gives you the opportunity of, one, reducing cycle time, so the cost of on designs is lower. It also offers the opportunity to make parts that weigh less to do the same thing, that use less of the primary material. An example we like to use has to do with an aircraft part. So this traditional machining way of doing it takes 8 times as much material as you actually end up with in the part. If you assemble it from a powder with electron beam heating to fuse things together, then you reduce the amount of material to 1.5 times what you end up with, and you reduce the energy use over the life cycle of that product by a factor of 3, because when you fly that around in an airplane, it takes fuel to fly weight. So there just is a host of opportunities across the manufacturing spectrum for doing things like this, for process intensification, for making everything we do more efficient. So there's a message there as well. We should look across the energy systems and as systems as a whole and look for the opportunities to use energy efficiently. Making it efficient is a big step along the way to reducing greenhouse gas emissions as well. So let me finish by just saying a word or two about the enabling science here. We, at the Department of Energy, we run a host of user facilities at the 13 national labs in the complex, the Science and Energy Complex, and then the 3 labs in the National Security Complex, Livermore, Sandia, and Los Alamos also do this as well. These are X-ray sources. They're used for materials characterization, neutron sources. The example that's shown here, that little turbine blade that's sitting in the middle there is shown next to the spallation neutron source at Oak Ridge. The blade itself was made by additive manufacturing. So this is one of the efficient manufacturing techniques. The image that's shown there is the residual stresses that exist in that blade after it's manufactured. Now, those of us that ride around in airplanes would like those blades to hold together. That's a good thing. And being able to understand the state of stress within them is a way to guarantee that the properties that you need are also there as well. I just will point out that virtually everything we do in the energy space at some point arose from the fundamental understanding of science. So the combination of catalysis, of nanostructured materials, of being able to close the design loop around materials properties that we want computationally, that is a huge opportunity going forward as well. And then I'll close with the idea that really advanced computing is totally fundamental to everything we do here. We've made lots of progress. That was, if you think about the last 2 decades, for example, on the national security side, once we stopped testing nuclear weapons for real, we began testing them in computing facilities. That demanded and led to a big advance in computing power. That, of course, immediately, once it was available, immediately got adopted by the scientific community. We're embarking on another version of that now, and that offers many more opportunities for another big advance in performance. And this will require us to understand a variety of new ideas, quantum computing, neuromorphic computing. These are ideas that are being explored with scientific discovery that might be based on quantum mechanics and the chemistry of materials and particle physics. The neuromorphic computing mimics the neurological processes in the brain. Who knows, we might actually begin to understand something about how our brains operate. There's a real potential there. Both of these really require development on kind of a decade scale for forward. This will involve both technology developments and systems developments and underpinnings and mathematics and science. And so there is something for all of us to do in this world. I would say that we're entering another period of really exciting potential performance in computing with great challenges that really do matter. So it's a great time to be working in this area. So in case you don't want to read all 500 pages of the Quadrennial Technology Review, though I do actually recommend it, it really is quite fascinating reading. Let me give it to you in 4 bullets. And then I'll note also that if your particular favorite technology area is not covered in enough detail in the main report, there are many individual technology assessments that are available on our website, energy.gov/QTR. So here's where we stand on the energy technology world. We've made lots of progress. It really is quite heartening to see the progress we've made and the fact that greenhouse gas emissions have gone down in this country in the last few years, so that's exciting. But there's lots more to do. This is a multi-decade endeavor that we're embarked on, and we need to work hard on it and stick with it over time. There's a huge opportunity space, both for individual technologies and for improved energy systems that use our ability to understand and compute our way through complex systems that will allow us to make these systems work much better in the future. We really do have to have a portfolio here. Research takes place in a spectrum of not knowing exactly which technologies and which approaches will mature the most quickly. So that needs to be fully stocked across primary energy resources, the ways we convert those into services, with lots of different system scales and time scales for application, and efficiency everywhere. We really need to make that a primary metric that we use in addition to cost going forward. And then to finish, the enabling science and computing capabilities are absolutely fundamental to all of this, and we can't imagine going forward at the pace we need to without them as well. So with that, I'll close and say thank you very much, and I'm happy to try to respond to questions if they're not too hard. Thank you.
Thank you very much for this really interesting talk, Undersecretary Orr. So we have microphones left and right. Please line up, and if you want to have a question, or you can submit it through the app if you are interested. So perhaps like until the first people come up, I ask a question.
Okay.
Global warming and the energy issues, it's a global problem. And so your ministry, as I understand, is also responsible for funding science and so on. So why don't we have more international funding available for collaborative science across the world? Mm-hmm. So I know there was a G8 had like a few little mm-hmm. things, but it's not on a big scale. It's a big problem. So
yeah, it is a big problem, and we're slowly edging our way toward to making the commitments to do something. I think the approach to the COP21 meeting in Paris in a couple of weeks with more than 150 countries now announcing goals for their particular settings, that's a start. I think we can actually look to the science community for some examples of how to do this. The CERN collaboration that produced the Large Hadron Collider and the Higgs boson results is one example of a big international collaboration. We're working on one now that involves neutrinos, and there is lots of conversation among research groups around the world. It's mostly funded in our individual places as of now, but you're probably right that there's room for more collaboration.
Okay. So actually, some questions were submitted. My device didn't work.
What we need is better communication.
Okay. So first question was very popular. Does the need for sustainable energy supply combined with climate change imply that nuclear energy use must increase?
Well, I think nuclear is an important component of the energy mix. Having a baseload source of electric power that has very low greenhouse gas emissions, really just from the steel and concrete in the plant, is an important component. But there are some problems we have to sort out. We have to deal with the spent fuel problem, and we have to deal with the cost challenges as well. But I do think it needs to be an important component going forward, and we need to work hard to make that happen.
Do you see a role of in-home batteries now to lower carbon emissions today?
Okay, so that's a very good question, the role of in-home batteries. So the question is, what service are those batteries going to provide? Now, for those that own an electric vehicle, for example, you can imagine that having a battery means that you could still be charged up to go to work even if the power's off in your neighborhood. I live in a neighborhood in California when I'm there where the wiring was installed in the 1910s, and it's iffy at times. So that would be a service that people might very well be willing to pay for. And the ability to run your house when the grid's offline is something that some people have generators now. So those are both services that have value. There's talk of being able to use this as a balancing component on the grid as a whole, but we'll need to figure out market valuation for the service that person has paid for the capital cost for and provide. And so all of this is a long-winded way of saying that, you know, I don't really know for sure how that's going to play out. I think it's a very interesting area and one that has a lot of potential, but much more to be thought about before we know for sure what happens.
Okay, so perhaps we also have time for like at least one question at the microphone.
So you spoke briefly about the Department of Energy Research Laboratories. What barriers do you see in transitioning the technologies developed at the laboratories into industry practice and making sure that industry needs are aligned with what's going on in the laboratories? Mm-hmm.
Yeah, it's a good question. We actually have put a fair amount of effort into this area of late. We've had several national commissions that have looked at the labs and looked at ways to streamline the relationship with industry both ways, with results coming out of the labs, but also making possible for industry to work with the labs. Actually, a quite significant component of the work that's done at the X-ray light sources, for example, is actually industry-sponsored as well, including beamlines. But we've also established in the science and energy part of DOE, we've established a new Office of Technology Transitions that's aimed at streamlining and coordinating and making it much more possible to build those links between the labs and industry. So we have more to do for sure, but you're right. The labs are this science and technology powerhouse, and we should leverage that both ways.
Okay, perhaps one quick question.
Yes, Takagi, what is your estimate on the future amount of the fossil fuels, future trend of the price, and how can we help with that?
So the question, I think the question is, what's the future trend for fossil fuels? This is the time where I should say, do not invest based on anything I'm about to say. If you look at my track record of investing, you would definitely not do what I say. So fossil fuels, because they provide an extremely valuable service in terms of energy density, they will be with us for an extended period. So we need to make sure that we use them as efficiently as possible. And then to the extent, for example, that methane stays in the electric power generation mix over time, we need to work on carbon capture and storage for that as well. Now, It actually is, because what comes out of a gas-fired power plant is cleaner than what comes out of a coal plant, that looks like it might even be a little less expensive there. So we'll need to balance those two, and over time the fraction of fossil fuels is likely to decline, but it will take a long time.
Thank you very much, Undersecretary Orr, for these interesting insights and showing us a little bit that our work has some influence on the world's problem. And thank you very much.
Important. Thank you all.